In this lesson, we're going to be introducing the idea of a polynomial function, defining a polynomial function, and looking at some familiar polynomial functions and some characteristics of certain types of polynomial functions. So let's start by figuring out what exactly these things are. The definition states that a polynomial function of degree n. So we name, and we'll talk about this, but we name our polynomial functions by the highest degree term that they have. So this is a function f of x equals a sub n, x to the power of n, plus a sub n minus 1, x to the n minus 1, plus dot, 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 plus a1x plus a naught. Okay, so what do all these variables mean? Okay, so, well, the a sub I, so the a's with a subscript, these are your coefficients. And so these coefficients need to be real numbers. So we're just saying that these an is some real number, an minus 1 is another real number, could be the same, not necessarily. A1 is a different real number, a naught is a different real number. They could also all be 0, so you don't have to have every single term in a polynomial function. The only key is that a sub n is not equal to 0, because otherwise it wouldn't be degree n, it would be degree n minus 1. Okay, n, so the exponents and these little subscripts are elements of the natural numbers. So they have to be between 1. For your exponents, those exponents have to be between 1 and 1, 2, 3, 4, 5. They have to be a counting number. Okay, so we have actually seen a bunch of polynomial functions before. And so what we're going to do is we're going to start by looking at some of the more familiar polynomial functions you might have seen. So let's look at what we're going to do is we're going to look at what the degree is. We're going to look at an example of it. We're going to name it, and then we're going to graph it. Okay, so we have a degree 0 function. Okay, well, what's an example of a degree 0 function? If we have a degree 0 function, that means we don't have an x, it's just a constant. So you could have, for example, f of x equals minus 2 would be a degree 0 function. Why is that? Well, because x to the 0 is going to equal 1. So that means the highest power of x is just a number, no variable at all. The name, well, this we would actually call a constant function. So it's a function that's defined as the same number all the time. Not really super interesting. And if we were to look at the graph of a constant function is always going to be a horizontal line. So it'd have to be not just any line, just a horizontal line is a constant function. Okay, so what does a degree 1 polynomial look like? Well, an example of that might be y equals 2x minus 1. Interesting. That sounds like a function we've seen before. This is a linear function. So a linear function is actually a degree 1 polynomial function. So we know how to graph some polynomials already because we know how to graph a line from Math 10, right? We do. I know you guys do. I believe in you. So this is our degree 1 polynomial. A degree 2 polynomial. Let's see if we know anything about that. That might be like a y equals x squared plus 2x plus 1 or something like that. That is, you guessed it, a quadratic function. We call it a quadratic function. So a quadratic function is a degree 2 polynomial. Hey, I was a little concerned. I had no idea what a polynomial was, but actually I know what a degree 0 polynomial function is. I've graphed those before. I've graphed degree 1 polynomial functions before, and I've spent most of pre-calculus 11 graphing degree 2 polynomial functions. And the graph of our degree 2 polynomial function looks like this. It's not the same as the one I wrote. It's going to be some kind of parabola-y looking thing. So let's move on to degree 3 polynomial functions. So a degree 3 polynomial function might be like y equals x cubed plus x. We don't necessarily have to have every term. So we don't necessarily have to have an x squared piece. We don't necessarily have to have a constant term. That's not always going to occur in our functions. The key thing is that we're just going to name it by the highest degree term. So this we call a cubic function. And you guys have actually graphed, we've seen the graph of one cubic function before because we looked at it when we did our transformation units, and that's the graph of y equals x cubed. So a cubic function could look like that. But cubic functions actually are a bit more diverse in appearance as well. So you could have a cubic function that actually looks like this. Doesn't necessarily have to just have that kind of flattened out point in the middle. It can go up and down and kind of have different sorts of turning points. And we're going to be talking a bit about the turning points because if you've noticed, constant functions don't have any, they're flat. Linear functions don't have any, they're straight. Quadratic functions have one turning point. Cubic functions could have no turning points, or they could have two. Could they have one? I don't know. We'll find out. It is possible. So let's look at a degree 4 polynomial. So now this could be y equals x to the 4th plus 3x squared minus radical 2 times x plus 1. The coefficients here don't necessarily need to be whole numbers. They could be fractions, they could be radicals, they could be pi. It doesn't matter. They just have to be some number, some real number. So this 4th degree polynomial does have a name. We call it a quartic, but often we'll just say degree 4 polynomial. And for higher degree polynomials, we'll usually just call them degree 5, degree 6, degree 7. And so if we look on Desmos and we just graph y equals x to the power of 4, it kind of looks like a parabola, only it's a bit steeper going up on the sides and it's a bit flatter at the bottom. So you guys, if you want to, can have a look at that on Desmos. So it's just like kind of like a flattened out parabola at the bottom and steeper sides going up. But our quartic could also look a lot of other different ways. So it could look like this. Would be another possible example of a 4th degree polynomial graph. Okay. So let's talk about some of the things these have in common. So polynomial graphs all have a domain that is x is all real numbers. So they all of the pieces of them take in any number. There's no x you can't plug into a polynomial graph. Okay. Number 2, they are continuous. So unlike our rational and radical functions, these exist everywhere in R. There are no gaps or breaks. And they're also smooth with no sharp curves. So not like an absolute value where it gets pointy. It's always going to be kind of turning around in a smooth way. And if you're planning on taking calculus, there's a specific word we're going to use called differentiable to describe this sort of smoothness. Okay? So what we are going to look at next is the end behavior of polynomials. So generally, when we're looking at polynomials, certain types, if we go back and we look, certain types of polynomials have things in common. So odd degree polynomials with an odd degree and polynomials with even degrees tend to behave similarly when it comes to the ends. Okay? So let's take a look. And this has to do with the fact that when you raise something to an odd power, it preserves the sign. But when you raise something to an even power, it comes out positive. Okay? So let's take a look at end behavior. End behavior is just what's the polynomial doing when the numbers get very, very big or very, very small. So first what we're going to look at is we're going to look at odd degree polynomials. And we are going to start with odd degree polynomials where we have a sub n positive. So what this means is we have a positive leading coefficient. So if you think back, remember when you guys were graphing quadratics, and if you have a positive number that's multiplying the x squared, it's a smiley parabola, and a negative number that's multiplying the x squared, it's a frowny parabola. We have to be, the number that's going to make the biggest difference about what happens at the ends is going to be the number that multiplies the highest degree term. Because as we get bigger and bigger and bigger and bigger and bigger, like we talked about with rational functions, the lower degree terms stop making a difference because powers are really, 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 really powerful. Okay, so let's take a look at we have a degree 1 function, and it goes like that. So it starts low, ends up high. If we have a degree 3, it might go something like this, but it's also going to start low and it's going to end high. If we have a degree 5 polynomial, it might bump around a little more, but it could start low and then kind of go up and then maybe go up again and end high. But the key thing is that the end behavior is the same. It's going to start in negative y. It's going to kind of start from negative infinity and go to positive infinity. Okay, so as x gets really small as it goes to negative infinity, f of x is going to also go to negative infinity. So as x goes to negative infinity, y goes to negative infinity. We're going down. And as x goes to positive infinity, as we get bigger and bigger and bigger and bigger, the y values are also just going to get bigger and bigger and bigger and bigger. And so this is just a mathematical description of the end behavior, but you can say when x is really small, like close to negative infinity, y is really small. When x is really big, y is really big. So what happens if our leading coefficient is negative? Just like with a parabola, when you had kind of flipped from a smiley to a frowny, this is going to flip what's happening. So if I have a degree 1, my leading coefficient is negative, it's going to go start higher and go lower. And if you think about what's happening with a linear equation, that leading coefficient is the number that's multiplying the x, which is the slope of the line. So this is really just what's happening with a positive slope versus a negative slope. If I have a degree 3 polynomial, same, we don't really need that arrow. Same idea. So we're going to start higher and then maybe we'll go lower. Doesn't really matter how many bumps. We can't have more than a certain amount, but we'll talk about that in a minute. Okay, but we're going to start from up and go down. And then if we have a degree 5 polynomial, similar, but possibly with a few more little bumps in it. We're going to start from high and go to low. So as x, with these ones, as x approaches negative infinity, our y, so f of x, is going to be getting bigger because we're having negative times a negative. And as x approaches positive infinity, our y values are going to be getting smaller. So it goes the opposite way as the other one. So we start high, go low, or start low, go high. So if you have a positive leading coefficient, you start low, go high. If you have a negative leading coefficient, you start high and you go low. Okay, so that is odd degree polynomials. Let's take a quick peek at what happens when we're looking at even degree polynomials. Okay, and just to be clear, even degree polynomials, and even there is a thing called an even or an odd function. That is actually a symmetry condition on a function. It is not the same as being an even degree polynomial. So when I'm talking about an even degree polynomial, that's not necessarily, if you've ever heard the term even function, they are not the same. Okay, these ones are a little bit simpler. So let's look at a sub n positive. So my leading coefficient is positive. Well, if I have a degree 2 function, then what do we have? We talked about that already. That is a smiley parabola. If I had a degree 4 function, it would have possibly a couple more bumps, but it would also have the same thing. So what happens here as in both directions, the positive and negative infinity, for even degree polynomials, the y is going to go up. We're going to get bigger. So even degrees are a little easier because really as you get smaller and you get bigger, the same thing is happening on both sides. If our leading coefficient is negative, we have degree 2. We talked about this already. This is our frowny parabola situation. And same with a degree 4 or a degree 6. It means that we're going to be opening kind of downwards with our arrows going downwards, even though we might have a little bit of a different look throughout the polynomial. And so we get that as x is going either to plus or minus infinity, it's either getting really big or really small, f of x is going to get really small either way we go. So it's just going to get small, small, small. Okay? So those are features that we can tell about polynomials, is what the end behavior looks like. Okay? We know what the degree is. We know what the end behavior looks like. Next, we're going to take a look at x and y intercepts, just like we did when we did rational functions and quadratics and probably pretty much even lines. Everything you've ever graphed, we talk about x and y intercepts, it seems. So our y-intercept, okay, that is your constant term in your polynomial if it's not in factored form. Or we can find our y-intercept or plug in x equals 0, because at the y-intercept, x equals 0, just like with every other function. For our x-intercepts, y equals 0. Okay, so we call these, we also have two other names from them. We can call them zeros of the function. So if we're talking about the function, we call those the zeros. If we're talking about the graph, we call it the x-intercepts. Or we can call it the roots of the equation f of x equals 0. Okay? And generally, when we're trying to find x-intercepts, we are much, much, much happier if our equation is in factored form. So we want it to be factored. Okay? So let's take a look at a quick example. Okay? Find the intercepts of the function of the graph of f of x equals x to the 4th minus x squared. Okay, so our y-intercept, we'll plug in x equals 0, which gives us f of 0, which is 0 to the 4th minus 0 squared, and that's just 0. So our y-intercept is 0. Now we're going to look for x-intercepts. So we have 0 equals x to the 4th minus x squared. We're not going to add x squared to both sides because we never divide by a variable. This is going to be x squared times x squared minus 1, which factors to x squared times x plus 1 times x minus 1. So the x-intercepts, we have 0, we have -1, and we have positive 1s at 0, 0, 1, 0, and -1, 0. Those are my x-intercepts from my factored form. Okay, turning points. So one of the tricky things about these functions is that they sometimes turn around. So a quadratic turns around once, a cubic sometimes turns around, sometimes doesn't, sometimes has like a turning point or a little bump. If we look back at our function, I'm just going to scoot you back up here. So a turning point would be like here, or here, or here, or here, or here, any place where the function turns around. So we don't have an exact number of turning points based on the degree, but what we do have is some limitations, okay? So if we have an even degree polynomial, because the end behavior is that you're going in the same direction, it means you have to turn around at least once, okay? So a degree n polynomial can have, okay, it can have from 0 to n x-intercepts. So think about a quadratic. A quadratic can have 0, 1, or 2 x-intercepts, and it's a degree 2 polynomial. So that means a quartic, or a fourth degree polynomial, could have 0, 1, 2, 3, or 4 x-intercepts. So it's possible that it doesn't have any x-intercepts at all, okay? And the number of turning points it could have from, well, it has to turn around. It can't have 0 turning points because our end behavior is that we're going in the same direction. So it has to have at least 1 turning point. And it can go up to n minus 1 turning points. So if you think a quadratic, it turns around once. It's degree 2. A quartic can turn around 1, 2, 3 times, but then it has to keep going off in the same direction. So here we can have from 0 to n minus 1 turning points. Okay, an odd degree polynomial, we have a little bit of a reversal here. So a degree n polynomial can have from 1 to n x-intercepts. So essentially, an odd degree polynomial has to cross the x-axis, and that's because, again, of the end behavior. So it starts low and ends up really high. So if you start at negative infinity, you're going way down, and you have to get to positive y's, you have to cross the x-axis if you're a continuous function. And in terms of turning points, it can have from 0 to n minus 1 turning points. So for both of them, the maximum numbers of turning points is 1 less than the degree. But an odd degree polynomial doesn't actually have to have any turning points. And we saw that with y equals x cubed. That one kind of flattens out a bit in the middle, but it doesn't actually turn around there. And actually being able to calculate that it doesn't turn around at all is something we get to do in calculus. So no spoilers. I'll leave it for then. Okay, last thing we're going to talk about is multiplicity of zeros. So this lesson is basically a big information drop. In the next lesson, we're going to be looking at how we take all this information and use it to actually graph some polynomials. Okay, so let's take a function. This one is easier to show with an example. So if we have f of x equals x minus 2 cubed, x minus 1 squared, times x, okay? So what happens is we have a root. In the area around a certain root, we are going to have certain things happening, okay? So this exponent tells you how it goes through. This is kind of like an x to the 1. So if this isn't 1, it crosses axis like a line. So it doesn't have to be straight, but it just goes straight through. Okay, this one crosses the axis like a quadratic, so this one turns around when it hits the axis. So like quadratic, and this cubed crosses axis like a cubic. So what happens is a root like this, x minus 2 cubed, means that at 2, let's see what this function would look like. Okay, it's positive, so we know that it's got degree 6 in total if we were to expand it. Don't need to worry about that for now. So let's say we have 2, 1, and 0. So that means we're going to cross the x-axis here. We just go straight through. This is our x equals 0. That's our x-intercept. This is our x equals 1, our x-intercept, and this is our x equals 2 x-intercept. So at the x equals 1, 0 x-intercept, we just go straight through. At the x equal 1 x-intercept, we cross it like a quadratic. So that means we go up, and just right around that root, it looks like a quadratic. It looks like something squared. So we go up, we touch that x-intercept, and then we turn right back around. If we were coming from the top, we would hit it, and we would turn right back around from the top. Now, at x equals 2, we're going to go through like a cubic. So it's going to kind of flatten out there for a minute and look like a cubic again, just right around that root. And then it's going to carry on doing whatever it was doing. So this is my multiplicity. So this we would call a root of multiplicity, or a 0 of multiplicity 3. And it acts like a little bit of a cubic just in that area. This we would call a 0 of multiplicity 2. And this one we would call a 0 of multiplicity 1. And it really is just, that's really just happening in the area around the root.